Welcome to this session on CCNA tutorial, Network Fundamentals. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step towards certification success. Today, we'll be covering Section 1.6, Configure and Verify IPv4 Addressing and Subnetting. We'll break down how IPv4 addresses work and how subnetting helps us organize networks efficiently. You'll learn what a subnet mask does, how to identify the network and host portions, and how to calculate ranges, block sizes, and usable addresses. We'll also look at how VLSM that allows networks of different sizes to share the same address space without wasting IP addresses. By the end of this section, you'll be able to read, design, and calculate IPv4 subnets confidently. IPv4 is a 32-bit addressing system that uniquely identifies devices on a network. It's written in dotted decimal format, like 1.2.3.4. Each address is split into a network part and a host part, based on the subnet mask. Computers work with binary, but we use decimal to make it easier for humans. Each octet has 8 bits, and each bit has a value that doubles as you move left. Starting from the right, the values are 1, 2, 4, 8, 16, 32, 64, and 128. That's why binary aligns so perfectly with IP addressing. To convert decimal to binary, start with the largest bit value, which is 128. If the number is at least that big, put a 1 and subtract. If not, put a 0. Then move to the next bit. If the remainder is 0, the rest are all zeros. For example, with 160, it's larger than 128, so we put a 1 and subtract 128, leaving 32. Then move to the next bit, 64. 32 is smaller than 64, so we put a 0 and move to the next bit. 32 is exactly the next bit value, so we put another 1 and subtract. Now the remainder is 0, so the rest are all zeros. The binary result for 160 is 101, followed by 5 zeros. To go from binary to decimal, line up the bit values and add up only the ones that match a 1. For example, if the first 2 bits are 1s, that's 128 plus 64, which equals 192. If all 8 bits are 1s, the total is 255. A subnet mask separates the network portion from the host portion. It's always written as 1s followed by zeros. For example, 255.0.0.0 is a /8 because the first 8 bits are zeros. The mask tells us the network ID, the host range, and the broadcast address. The network portion identifies the subnet. It's the same for all devices in that network and shown as 1s in the subnet mask. The host portion identifies the specific device. It's unique for each host and shown as zeros in the subnet mask. Think of it like a street name and a house number. The subnet mask decides where the split happens. 1s mark the network part, and zeros mark the host part. For example, for a /16 subnet mask, the first 16 bits or 1s define the network, and the rest identify the hosts. The network address or network ID is the first address in a subnet. All host bits are set to 0. It identifies the entire subnet and can't be assigned to a device. Routers use it to route traffic between networks. To calculate it, perform a logical AND between the IP address and the subnet mask. Wherever the mask has a 1, keep the IP bit. Wherever it has a 0, replace it with 0. For example, with 1.1.1.1/16, the mask is 255.255.0.0. Applying the AND operation gives 1.1.0.0, which is the network address, the starting point of that subnet. The broadcast address is the last address in a subnet, where all host bits are set to 1. It's used to send a message to all devices within that subnet at once and can't be assigned to a host. To calculate it, keep the network bits the same and set all host bits to 1. For example, with 1.1.1.1/16, the broadcast address is 1.1.255.255, the final address in that subnet. The usable hosts are all the addresses between the network ID and the broadcast address. To find the usable range, simply add 1 to the network ID to get the first usable host, and subtract 1 from the broadcast address to get the last usable host. For example, If the network is 1.1.0.0/16, the broadcast address is 1.1.255.255. That means the first usable host is 1.1.0.1, and the last usable host is 1.1.255.254. Every address between those two can be assigned to devices inside that subnet. Subnetting is the process of dividing a large network into smaller and more manageable subnetworks. We do this by borrowing bits from the host portion of the address and turning them into network bits. The main goal is to use addresses more efficiently, reduce broadcast traffic, and improve performance and security. When we borrow bits from the host portion, we create more subnets. The number of subnets equals 2 raised to the power of the number of borrowed bits. For example, imagine a network 1.1.0.0/16. If we borrow 2 bits, the new prefix becomes /18. Now we have 4 smaller subnets instead of one large network, each with its own network ID, host range, and broadcast address. When you need to create a specific number of subnets, follow 3 steps. Step 1. Check how many subnets are required. Step 2. Find the smallest power of 2 that is greater than or equal to that number. Step 3. Add that number of borrowed bits to the original prefix to get your new subnet mask. Let's go through an example. We want to divide a /8 network into 3 subnets. We test powers of 2. 2 to the power of 1 equals 2, which is not enough. 2 to the power of 2 equals 4, which covers the requirement. So we borrow 2 bits, giving us 4 subnets in total. The new prefix becomes 8 plus 2, which equals /10. That's how we find the number of borrowed bits and the new subnet mask. To find out how many hosts each subnet can support, we use this simple formula. 2 raised to the power of host bits minus 2. The -2 is important. We remove one address for the network ID and one for the broadcast address. Let's look at an example. If we have a /24 network, there are 8 host bits left. 2 to the power of 8 equals 256, and after subtracting 2, we get 254 usable hosts. When you're asked to design a subnet for a specific number of hosts, the goal is to find the smallest subnet that can fit them all. Use the formula 2 raised to the power of host bits minus 2, and test until the result meets or exceeds the required number of hosts. For example, if we need at least 100 hosts, 2 to the power of 6 equals 64, which is too small. 2 to the power of 7 equals 128, which is enough. That means we need 7 host bits. Now, to find the prefix, subtract 7 from 32. 32 minus 7 equals /25. A /25 subnet supports 126 usable hosts, which is more than enough for 100 devices. The block size shows how big each subnet is and how much we count up to reach the next one. We find it by raising 2 to the power of the number of host bits. In a /25 network, the subnet mask is 255.255.255.128, which gives a block size of 128. This means network IDs appear at multiples of 128 in the last octet, 0 and 128. The first subnet runs from 0 to 127, and the next starts at 128 and ends at 255. Each subnet provides 126 usable host addresses. Variable length subnet masking lets us create subnets of different sizes instead of equal ones. For example, from a /24, you could create a /25 for 100 users, a /27 for 25 users, and a /30 for a point-to-point link. To summarize, the subnet mask defines where the network portion ends and the host portion begins. The network address has all zeros in the host part, and the broadcast address has all ones. Usable hosts are simply the addresses in between. We calculate the number of subnets by taking 2 raised to the power of the borrowed bits. The number of usable hosts is 2 raised to the power of the host bits minus 2. The block size is also found using 2 raised to the power of the host bits. And with VLSM, we can use different subnet sizes within the same network to make IP addressing more efficient and avoid wasting space. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below and I'll be happy to help. In the next section, we'll cover private IPv4 addressing. We'll look at the different IP classes, the reserved private ranges, and a few special purpose addresses such as the loopback. This will help you recognize which addresses are used inside networks and which ones are meant for public communication.